Assalamu alaikum. This is a continuation of our previous lecture. So in this lecture, we will, the title is the power of the amplitude modulation. So we actually calculate the power of amplitude modulated signal. Okay. So in previously, we did actually various kinds of amplitude modulation. We find the modulation index. We find what is the condition in an envelope detector, actually just envelope detector. And we find the condition where the tau, the time constant of the envelope detector, what should be its range. It should be in between the time period of carrier and the time period of the message signal. So it means the tau should not be very fast, or tau should not be very slow. If it's very fast, then it actually loses of the detection, and if it's very fast, then it's actually discharge very. If tau is very large, then it's actually very slow. Then it cannot detect the envelope, and if it's very very small, then it's discharged very fast. Then it's actually, instead of detecting envelope, it start detecting the carrier. Okay, now we will actually calculate the power of the AM signal, amplitude modulated signal. So let us see what was actually our modulated signal xt. We already seen it. AC 1 plus Ka mt cos 2 pi fct. So this is actually our modulated signal. In the modulated signal, it has actually, we have seen that it has two parts. One is a AC cos 2 pi fct plus AC Ka mt cos 2 pi fct. So the modulated signal have two parts. One is the pure carrier. So this is actually a pure carrier, and this part is the modulated carrier by the message. So carrier modulated by the message. We have seen these two individual part from the Fourier transform section, right? So what we will do in this section, we want to find the power of the amplitude modulated signal, for which we will actually find the power of a pure carrier. We will find the power of the modulated carrier. Then we will actually add up. We actually add them together to find the total power of the AM signal. So here let us find. So which part we want to find first? Let us find the. Okay, let us find the modulated carrier first. Okay, so what is the carrier modulation or the modulated carrier? Consider. So here two part. So here two components. So component one. So this is one component. This is another component. Okay. So in component one, what is actually our signal? AC Ka mt cos 2 pi fct. This is actually the here. This is actually our modulated carrier, where this one is actually a sinusoid with amplitude of, this is actually this part. This part is what? This is a sinusoid. With amplitude AC K A. So you see this is a time varying, right? So it's actually a sinusoid with a amplitude AC AC K A MT, which MT. So if this is the case, then the MT is a varying at much slower than this is a message signal, right? So we can say that MT is varying at much slower rate than the carrier one. So cos 2 pi FCT means actually we know that FC is much greater than the FM. If this is the case, then instantaneous power can be approximated as, so if this is the case, then instantaneous power, so instant power can be approximated as, if this is the case, then instantaneous power can be approximated as half of this K A square AC square M square. So this was, we assume that this is the amplitude of this carrier signal, which is, but the MT itself is a time varying signal where there is rate is much smaller than the carrier. Because of this, then we can find the instantaneous power, so which can be approximated as the following, now what is the average power? If this is the instantaneous power, what is the average power? So what is the average power? So to find the average power, easily find the expected value of this. So expected value of these is this. If this is the case, then we can take it out. So half Ka square C square. This portion is actually pure constant, means expected value of M square T. If we can find the expected value, we can find the complete value here. Okay. So what is this part? This part is actually the power of the message signal. Expected value of M square is nothing but the power of the message signal, which we can write it as a PM, power of the message signal, PM. If this is the case, then this find as half Ka square AC square PM, where PM is the power of the message signal, MT, power of the message signal. So this is the power of the message signal, MT. Power of the message signal, MT. So the total power. So what is the, okay, so this is the case one. So this is one carrier modulated signal. So this is the component one. So let's find the component two. Okay, AC cos. So this is actually power component two. Component two, the second component. So what was our second component? Our second component was AC cos. Okay, so our second component was AC cos by FC This is actually a pure carrier, right? This this signal is nothing but the pure the second component or first component, however, anyway you like to denote it. This component is nothing but a pure signal. So if this is the case, we already know what is the power. So we already know the power is nothing but the so we can see the okay, what is the power for this one? The power is nothing but the half a square, half AC square, right? Okay. So this is the case because we derived this signal earlier from the power and energy of any signal. So you can, if this is a constant, you can find the power of this signal. Okay, then what is the total power? So what is actually the total power? Total power of AM signal is what? Half AC square plus half AC square K square and PM. Okay, the first component and the second component, we just add up to find the total power. Okay, so if this is the case, what is the efficiency of this? So what is the efficiency? The efficiency efficiency will be nothing but the total power to the power in carrier modulated by message. Actually this portion, total power to this portion, because the first portion, these do not contains any message, it's only the carrier and do not carry any information. This is a pure carrier, and so this is a pure carrier and do not contain any information. If it do not contain any information, means this is not a useful for the message. So we actually do not consider it. So what is the total power? So the total power is nothing but half of AC square, which is actually 1 plus Ka square PM, right? And carrier modulated, which is actually half AC square Ka square PM. Okay, which is nothing but, so this portion cross Ka square PM and 1 plus Ka square PM. Okay, so this is the efficiency of the amplitude modulated signal. So now consider the message signal is a sinusoidal. So message signal is is sinusoidal. In that case, what happens to the MT? So MT can be expressed as AM cos 2 pi FMT, right? So what will be the power? So PM is the half of AM square. Okay. If this is the case, and we also know the modulation index. So this is the power, and we also know that the modulation index mu is nothing but Ka AM. We actually find it in earlier, right? If this is the case, then what is happened? So half of mu square is nothing but half of, from here, half of Ka square AM square. Which is actually half of AM square is PM. So Ka square PM. So put back this for to this efficiency. Put back this efficiency becomes Ka square PM and 1 plus Ka square PM. This value we put here. Now 1 plus Ka square PM. Yeah. Now we put the, we substitute this with the half. Okay, so Ka square PM, which is Ka square PM, which is actually half of mu square, then 1 plus half of mu square, which is actually mu square 2 plus mu square, which also can be written as 1 minus which also can be written as, which can also be written as 1 minus 2 plus mu square. Okay, now here, so we find it. Efficiency of the amplitude modulation is 1 minus 2 by 2 plus mu square. Here we can clearly note that if mu is increasing, then this value is decreasing, which ultimately gives this total value increasing. So if mu is increasing, efficiency also increasing. Okay, if mu is increasing, then efficiency also. Means by increasing the modulation index, you can increase the mu, or by increasing the modulation index, you can increase the efficiency. Okay, so what is the maximum value for envelope detection? So we already know it, right? This condition. We already know that for envelope detection, maximum mu max, for example, maximum value of mu is equal to max is 1. We have seen that if mu value is equal to 1 or less than 1, then it becomes the undistorted. The envelope becomes, otherwise it becomes over means actually if mu is greater than 1, we know this is actually a condition of overmodulation. It's actually overmodulation where the envelope distortion happens, or envelope distortion happens. So for no envelope distortion, the maximum of mu can be 1. Okay. So if maximum mu can be maximum value, so what is the maximum efficiency? Max. So maximum efficiency can be, we know from here, the maximum efficiency, if I use this equation, which is 1, 2 plus 1, the mu value. I'm putting the mu value, maximum mu value. So 1 by 3. So that is actually the maximum efficiency in amplitude modulation. So this is actually maximum efficiency of amplitude modulation, which is actually, what is 1 by 3, which is nothing but 1 by 3 is 33%. Means 67% is wasted. 67% of the power is wasted. This is very poor. This is very poor. Efficiency is very poor, and 67% of the power is wasted. 67% of the power is wasted. So all this problem actually happens because of what? Can you trace back where this power wasted? Here it got wasted. When we calculated the efficiency, you see, total power is in terms of what? Power in the carrier modulated by the message. Means actually we considered this portion only. We didn't consider this portion. So this carrier is transmitted, but it's not carrying any message. So the distortion, so the efficiency loses. So how we can increase the efficiency? By reducing the power or suppressing the carrier. So what is the solution to increase? Solution. What is the solution? Solution is to reduce the power, reduce the carrier power, or suppressing. Suppressing the carrier. So this is not a good solution to reduce the power because it's another consequences. Okay, so suppressing carrier will be the solution, which actually will lead to our next topic, suppress carrier. So here ends our this topic. Assalamu alaikum.